let's talk about what an operon is. An operon is, again, when genes are grouped together because they all have related functions. And there's going to be a couple of important sites on an operon. So on an operon, I think we could find a promoting site, or a promoter. What the promoter is that's going to be the site for where the RNA polymerase will bind. Now, what does RNA polymerase do? Can someone remind me? Okay. We just tested on this like last week. Yes, so it codes for the mRNA, right? It makes your mRNA. So this is the enzyme that makes mRNA. Right? So on this little drawing up here, can you tell me where RNA polymerase would bind? Would it bind at my gene 1, gene 2, gene 3, my stop sign, or my little circle here? Okay, good. So we would call this little region right here the promoter. So RNA polymerase is going to make an RNA transcript out of all of this DNA right through there, which would be great. Now, one thing you'll notice here is that this single promoter will control all of these related genes transcription. And again, as you can see, you are going to transcribe all three of these, or all of the genes, I should say, at one single time to make a long strand of mRNA that contains multiple genes. Cool. That means that when we transcribe this DNA right through here, we transcribe it as one big piece, even though it's containing different genes. Do you see introns or exons in this at all? No, because we're talking about bacteria. Remember bacteria? No introns and no exons. So all of the DNA that they transcribe is good to go. Good? I want to talk about one more important region that's in your promoter region, and that is the operator. This again is a site within the promoter. And its function is going to be the location of an inducer protein or a repressor protein. So this is a DNA binding site of a repressor protein. or inducer protein. What does repress mean? To start or to stop?
Stop.
So a protein that causes a stop of transcription. And what does induce mean? So this would start transcription. So maybe right here, going back up to your notes, it might be wise, because we really haven't talked about the tryptophan model yet. Why don't we just say that this is a general metabolic pathway? And then I'll say that I'll go into the specific ones in just a second. Simple. So the first thing I want us to recognize is that there's this region right through here, and this represents your region that is the promoter region. So there's your promoter. Of course, this is representing a strand of DNA or a piece of DNA. Cool. And let's say that this entire sequence that is the promoter and these series of genes that you're seeing right through here, all the way to the very end, is known as the tryptophan. So we're going to talk about the tryptophan operon. Now a couple things to mention about bacteria is that for bacteria, their tryptophan operon is always on, but can be turned off. So tryptophan is an amino acid, one of 20. The symbol for it is W. And tryptophan is not common in media where bacteria can be found, so a lot of times, since they'll be needing tryptophan, an important amino acid, they will be making it themselves, right? Which means they're going to need a series of enzymes to do a series of reactions to convert something into their tryptophan. Okay, so tryptophan's not always around, and so therefore this enzyme series, this operon, would always be on. But what would happen, in theory, if the bacteria started growing or you transplanted the bacteria onto a media, onto a plate that was containing tryptophan? Would they need to make it anymore? So it's always on, but it can be turned off if they encounter tryptophan.
So it's not always on?
It's always on, except it can be turned off. So it's always on until it is repressed.
And the they is,
Do what?
like you say, if they encounter.
If bacteria encounter. So it's also, when I say that it's always on, I mean it's always on except for the couple of little moments where tryptophan is in the media, which is not very common. So this would represent not just any type of an operon. This would represent a type of operon that is, again, mostly on but can be turned off. This would be a repressible operon. Now, one thing we'll see here is that within our promoter region, we mentioned this earlier in the notes, there's your little operator right there. There's your gene 1, gene 2, gene 3, gene 4, and there's gene 5 to make your different enzymes, E1, E2, E3, E4, and of course E5. So your mRNA that's made has sections for each of those enzymes. This, of course, is the mRNA. Remember, you transcribe the entire set of mRNA for all 5 of these enzymes at one given time. Right? So right here, these would represent the enzymes of protein synthesis. Or I should say, I'm sorry, not protein synthesis, tryptophan synthesis. The enzymes of tryptophan synthesis. Good? Now what we have here, of course, this would be your RNA polymerase. You can barely see it, but there it is. And that means that you have to have like kind of your start region, and there would be your stop region, so you can see the RNA polymerase at the very end there. It's transcribed the entire set of these genes. And again, this is the type of operon that is always on, but can be turned off if tryptophan is present, right? Now, think about it logically. This is kind of like a negative feedback mechanism. If there was anything in the world that would turn this off, what do you think it would be? It makes sense that it would be tryptophan. So if tryptophan comes into the media, tryptophan would obviously be turning it off, right? So this represents a negative feedback mechanism in which tryptophan, W, can act as a repressor in order to turn off transcription of the tryptophan enzymes. So again, that's a negative feedback model.
So what exactly, like, this might be a stupid question, what exactly are, like, the tryptophan enzymes doing? They're just, like...
They're taking, like, some other amino acid and running a series of organic reactions to it to do this, to, like, a bunch of interconversions to get you tryptophan. It's like they take this shape and they start messing with the shape in such a way that now you've got something completely different, and that something completely different is tryptophan. So if you already have, but if you have a media that contains tryptophan, you don't need to waste your time doing that, because obviously you already have tryptophan. So what you'll see here in your operator region is, do you see this little fit that we got going on right there? Y'all see that, right? There's like these holes, or this opening, right? It's like there's going to be this perfect fit that would occur. And you actually do have a repressor. So there's your repressor molecule. But do you see how this shape is? It's not going to fit in there. So this represents your inactive repressor. So inactive would mean that it doesn't work, right? So this is not going to be able to repress this protein, or this operon. Sensible? Kind of? Okay. Great. Now let me show you something a little bit different. I'll let you draw this out real quick. Make something very, very simple. And you can keep this right next to where you just were, because this right here is still the tryptophan operon.